For this next portion of our lecture, let's take a look at pump efficiencies. When we talk about a pump's efficiency, what we're really talking about is how well the pump can take the electrical energy, right, from a wall outlet or from an industrial power supply, transfer it through the motor, through the geometry of the pump, and into the hydraulic motor. That is to say, when I plug in my pump into the wall, what percent of the electricity, of the energy that motor uses, that pump uses, actually ends up in the hydraulic fluid. Now, we have three different types of these efficiencies. However, the overall efficiency is really just the first two put together. Let's take a deeper look at the volumetric efficiency and the mechanical efficiency. We've actually already seen the volumetric efficiency, right, labeled as this mu sub v, and it is a measurement of the amount of leakage that takes place within a pump. Again, we've already seen this. It is found by taking the actual flow rate of the pump, Q sub A, which is found experimentally, and dividing it by the theoretical flow rate of the pump, Q sub T, which is found mathematically using the equations from the previous videos. Looking at some typical efficiencies, we can see that gear pumps and vane pumps fall in this roughly 80 to 90% range, while piston pumps are highly efficient. There is very little leakage within piston pumps. Mechanical efficiency, on the other hand, indicates the amount of energy loss for reasons other than leakage. This includes things like heating of the motor, friction within the motor, and various other effects that cause us to lose energy in the process of converting that energy into hydraulic energy. Now, the equations here are a little bit more complicated than the volumetric efficiency. As such, I've laid them out for imperial up here in the top row and metric on the bottom. We'll use metric to explain them, but they are essentially the same equations, but imperial just has a few extra constants that you have to multiply or divide them by. So, starting off, mechanical efficiency is indicated with a symbol mu sub m, right? So mu sub m for mechanical and mu sub v for volumetric. Again, looking at the metric equation here, we can see that it is P times Q sub T divided by T sub A times N, where P is the discharge pressure, either in PSI for the imperial and pascals for the metric, Q sub T, which is, again, the theoretical flow rate, either in gallons per minute or cubic meters per second. T sub A is the actual torque to the pump, right? And we'll learn a lot more about torque in our motors class, but torque is sort of the oomph behind your motor. For imperial, it's measured in inch-pounds, and for metric, it's measured in newton-meters. And N is our pump speed. For imperial, N will be in RPM, or revolutions per minute, and for metric, N will be measured in radians per second. To get our actual torque, we can take the power that our system uses, so either the horsepower of our motor or the watts of our motor for metric, and divide that by 2 times pi times the speed that our pump is running at in either RPM or radians per second, and then divide that value by 60. Using these equations, we can calculate both the mechanical efficiency, right? That is to say, what percent of energy is not lost due to reasons other than leakage, and the volumetric efficiency, mu sub v, right? That is the amount of energy that is lost due to leakage, and we can find the overall efficiency of our pump, which, after dealing with that ordeal for the mechanical efficiency equations, is actually pretty simple. We just take our volumetric efficiency and we multiply it by our mechanical efficiency to get the overall efficiency of our pump. Taking a look at a few of the pumps that we've covered in this lecture, let's look at some overall operating metrics of these types of pumps. First, looking at pressure, right, in units of PSI, we see that the highest performing pumps are the axial and radial piston pumps. which can operate up to 12,000 psi. This drops off a little bit with external gear pumps and vane pumps, and finally internal gear pumps, which have the lowest amount of pressure that they can handle or output. For speeds, that is the RPM of the motor that these are running, we see a similar trend, where the external, the internal gear pumps and the vane pump all fall in the similar 1,000 to 2,000 range, while the axial and radial piston pumps can run at a slightly higher speed. The important thing here is the overall efficiency, right, as we just discussed, for each of these types of pumps. We notice that the lowest efficiency is in internal gear pumps. There's a lot of leakage and there's a lot of losses in the motors. This improves slightly when it comes to external gear pumps. It improves slightly more when it comes to vane and radial piston pumps. And finally, axial piston pumps, which are the most efficient types of pumps you can buy on the market. Now note that this is reflected in the cost, where piston pumps typically cost substantially more than external and internal gear pumps, with vane pumps sitting at a somewhat middle rating. The flow capacity is also an interesting metric to look at, right? We can see that internal gear pumps and both types of piston pumps have a very high flow capacity in gallons per minute. External gear pumps are a nice mid-range, right? And finally, vane pumps, which do not pump a lot of fluid at a high rate. Let's examine an important part of pump efficiencies, which is how they're reported on the pump's datasheets or nameplates. When you buy a pump, they will often include graphs that describe their efficiency at various pressures. While this looks a little complicated, let's break it down and understand what it's telling us. On the x-axis here, we can see that we have the pump input speed in RPM. That is how quickly we're spinning the motor attached to our pump. We also have two sets of curves here. The solid lines represent the volumetric efficiency, and the dashed lines represent the overall efficiency. The reason that there's two is that one curve, for both of these it's the top curve here, represents the pump operating at 3,000 psi, and the bottom curve represents the pump operating at 5,000 psi. We are probably more interested in the overall efficiency for our pump, so let's take a look at how these pumps perform. Notice that the peak efficiency is not when we're pumping the least amount of fluid or the most amount of fluid, right? The speed is not at a minimum or maximum, but actually somewhere in between. Pumps are typically designed for a specific RPM or pump input speed, and either going below or above that speed will reduce the efficiency. We also find that changing the pressure can cause this metric to change. For our 3,000 psi curve, that is this dashed line here, we note that the most efficient the pump can be, at around 89%, is at about 1,700 RPM. However, when we increase the pressure to 5,000 psi, our efficiency actually goes up to 90%, but now we have to run it at close to 2,200 or 2,300 RPM to reach that peak efficiency. Let's take a look at another type of graph you may find on the pump's datasheet or nameplate. This graph here compares the pump input speed in RPM with both the pump input horsepower, so the power we're putting into the pump, as well as the flow rate coming out of the pump in gallons per minute. Now this double axis may seem a little confusing at first, but what I want you to imagine is that this in reality is just two graphs laid on top of one another for compactness. At first a little confusing, but once we break it down, it shouldn't be too bad to read. These two top lines up here that are running nearly in parallel pertain to the GPM axis, right? We can see this very top line refers to the output gallons per minute at 3,000 psi and the output gallons per minute at 5,000 psi, right? So these two lines are talking about how the GPM, right? So this axis here changes when we change the pump input speed. We can see that changing the pressure doesn't really affect the pump output gallons per minute, right? From going from 3,000 to 5,000 psi only slightly decreases the pump output in gallons per minute. What really changes the pump output is the pump input speed, that is, how quickly our motor is spinning, right? By spinning it faster, we get much more gallons per minute. The bottom two lines here, which are not parallel, are referring to the horsepower axis. So ignoring this pump output GPM, so these numbers here, and instead looking at these numbers here, this axis, this tells us that by changing the pressure, we drastically change the input horsepower required to run this pump, right? If we run this pump for 3,000 psi, and maybe let's say, for example, 2,000 RPM, our pump input horsepower is going to be just below 100 horsepower. Now, if we instead up our pressure, right, if we resist that flow more and come up here to 2,000 RPM, right, we don't change the speed of our pump, you'll notice that the pump input horsepower falls right about here, which totals to about 150 horsepower, right? So by raising the pressure by 2,000 psi, we've increased the pump input horsepower, right, the power that this pump is burning through, by about 50 horsepower. Let's take a look at a somewhat disturbing datasheet graph here for a variable displacement pressure compensated vane pump. We can see that we have, well, a lot of stuff going on this graph, but when we remember that all this is several graphs laid on top of one another, we can slowly start to break down what this is talking about. So, on the x-axis here, we notice we have psi and the outlet pressure reported in both psi and bar. Again, this is the same axes, it's just giving us both units so that we don't have to convert, whether we're working in psi or bar. On the y-axis, or I should say the y-axes, we have flow rate in US gallons per minute. We also have efficiency in percent, represented by this bar over here. So for example, this number could mean either 70% efficient or 70 gallons per minute, depending on which of these lines we're looking at. Over here on the right, we have a power axis. So this axis is talking about kilowatts, and this axis here is talking about horsepower, but they're both measurements of power. Now that we know what axes are on these graphs, we can figure out which of them are actually useful to us by choosing a specific line to look at. Let's, for example, look at this volumetric efficiency line, up here starting near 100 and then slowly dropping down. Volumetric efficiency tells us that we're looking at the efficiency axis, so this guy here, and these numbers are going to be in percent. We can see at a outlet pressure of either about 20 bar or 200 psi, right? Both of those are the same. They've just been converted between units for us. Coming up here, we see that the volumetric efficiency is actually almost 100, right? We are almost perfectly efficient here. There's almost no leakage. But as we increase our pressure, the efficiency begins to drop. Right? If we look right here at this vertical line at about 2,000 psi or 140-45 bar, we can see that our volumetric efficiency drops to about 90%. If we wanted to know the effective output flow, right, of our pump at various pressures, we could look at this line running along here. right? So again, our x-axis is just one thing. It's the pressure, either in PSI or bar, right? We can choose. And our y-axis, right, we're looking here at, okay, output flow, which means we're coming over here and we're looking at the flow rate in US gallons per minute, right? Ranging from 0 gallons per minute up to 100 gallons per minute. We notice that the flow rate actually doesn't change much, right? At about 25 bar here, I'll just choose to work with bar, our output flow rate is roughly 30 US gallons per minute. Coming over here to the right and increasing our pressure to, let's say, 175 bar, we notice that we start getting a steep decline in the flow rate, right? Tracing that horizontally over here, our volumetric flow rate in gallons per minute drops to about 25 gallons per minute, and then sharply drops off after there from about 75 bar to 180 bars maybe. Yeah, somewhere in that range, where we get a sharp drop off in flow rate. Now, we've learned about many different types of pumps, but how do you actually choose between these pumps? How do you actually build a hydraulic system from scratch? Well, let's go through a short to-do list for building our hydraulic system. And the first thing we always want to start with is selecting an actuator, right? Which will typically be a cylinder, like the ones you use in your lab, right? This will be based on the loads and the size of what you're wanting to lift, but you'll be able to select one of these based on, am I lifting a car? Am I lifting a person? Am I lifting equipment? What am I doing, right? The next step is to determine the flow rate requirements. If we call back to this slide over here, we talked about we can figure out flow rate depending on how quickly we want our piston to extend, right? We know the volume that we want this guy to fill in the time that we want it to fill it in, so we can figure that out, right, by taking the volume of the piston and dividing it by whatever time we want it to fill in, or more specifically, the area times the distance divided by the time to get a required flow rate. Next, we will select the system pressure. This ties in with the actuator's size and the magnitude of the resistive force produced by the external load on the system, right? This also involves the total amount of power we will have to deliver to the pump. Remember, the pressure on an actuator will govern how much force it can output, while the flow rate determines how quickly it can output that force, right? Our pump selection actually starts at the other end of our hydraulic system. I want to lift this load, and I want to lift it this quickly, and the load is going to weigh or exert a force of this much, right? That tells us our flow rate requirements and our pressure requirements. Once we know those, we can determine the pump speed, right, from the flow rate requirements, and we can set the pump pressure, or whatever pressure limits our pump needs, based on the forces from our external load. Together, this sizes the pump. Here's a quick recap for a few different pump types and what they're best for. External gear pumps are cheap and they're good for high pressure and clean fluids. They don't do well though in that they're noisy and they don't handle solids very well. Inner gear pumps, or internal gear pumps, work well for viscous fluids and compact systems. However, they don't have great pressure tolerances and they don't work well with solids as well as the external gear pump, right? If you do need to handle solids, lobe pumps work very well here, right? They're sanitary and they can be used for things like cleaning fluids with slurries or solids in there, and they're very easy to clean themselves. However, they're bulky, they operate at lower pressures, and they can be costlier. Gerotor pumps are good for lubrication and compact applications, right? They're quiet, they're efficient, and they're compact, but they have very limited pressure and flow, and they wear down pretty quickly. Screw pumps are great for high viscosity and high pressure applications. They're smooth, they're quiet, and they're efficient. However, they are very expensive and very sensitive to solids. Right? So the actual type of our pump is going to be based on the application. Finally, once we know the flow rate requirements, the pressure requirements, the size of the pump, and the type of pump we need, we can select a reservoir as well as the other types of miscellaneous materials such as plumbing, piping, valves, filters, strainers, and other types of miscellaneous components.